Hello folks, how's everybody doing today? Hope you're doing fine and you didn't get any virus out there that's flying around apparently. Today we have a great day, and first of all I want to remind everyone we have a conference in Lusaka, Zambia. We've been advertising this for a while, so if you want to go, you got less than a month to pack your bags, buy your tickets, and make your reservations, hotel reservations, etc. Right? Want to remind also people that we've uploaded our book, known as the Rope Hypothesis, and it's a free book. You can download it at ropehypothesis.com. And what it'll allow you to do is become familiarized with what's happening in this channel, especially the rope model of light and gravity. Okay, it'll bring you up to speed, and it's a pretty easy book to read. I think it's heavily illustrated, so it's free. So if you're interested in physics, download it. Whether you believe in it or believe in the rope model of light or not, you will get a different view of the universe. That's for sure. So if you want to be picked, your interest, you want your interest to be picked. This is the right theory for that. Okay, and yeah, we always ask anyone who can translate, has got a second language, to contact us at tokakaka@hotmail.com. And if you want to offer to translate it, we'll be glad to help you out in whatever way we can. Okay, today I was again going to talk about something else, but I had a lot of comments, a lot of criticism, a lot of questions, and those need to be clarified before we move on. A lot of the people that come here, they don't know what the channel is about. And so a lot of things that they hear for the first time hit them in their ears, and they say, or in their eyes, right? And they say, no, something's wrong there. And it's because they haven't been around enough to understand what the channel is about. They don't know what the scientific method proposed here is about. They don't know what science proposed here is about. We're known as rational science, and that distinguishes us from irrational science, which we have out there today. If you go to general relativity, you'll find nonsense such as black holes, Big Bang, space-time, four-dimensional space-time, unimaginable four-dimensional space-time. You go to quantum mechanics, you find even more garbage. You find particles can be at two places at once, or many at one place, many particles at a single place. You'll have wave packets, unimaginable wave packet. The particle itself is a vibration of a field. And so you have all this nonsense with which the so-called mathematical physicists purport to explain the mechanisms Mother Nature uses out there to run her shop. And this is what we're criticizing. We have a rational proposal, a rational alternative known as the rope hypothesis. With a rope, we can explain magnetism, gravity, light, electricity, the workings of the atom in a rational way. What do I mean by that? I mean that we're going to be using objects and we're going to make a film. We're going to illustrate it for you. And you look at the mechanism, you say, yes, I understand it because it's straightforward. So you will understand it. Now, whether you believe it or not, that's a separate issue. Okay? But in the case of quantum mechanics, it's admittedly by the people in quantum mechanics, among them Richard Feynman, Nobel Prize, I think 1965, saying that no one understands quantum mechanics. No kidding. Okay, so today I'm going to address a lot of the questions, issues that came up, criticism, objections, etc. And I'm going to start with one fellow who put a comment, which I need to address first. And he said the following. He said, if I can get this name here. Bill, I say this, right? I say in my last video, I said, now you can see why it goes slower through glass than through air. I was talking about light. And that was an unfortunate statement. Yeah, and so he said, I'm now confused. Does light change color when it goes through the medium or not? Please clarify. Yeah, when I said that, what was going through my mind is not what came out of my mouth. Okay, I want you to know that. You're right in slapping me, okay? What happened was I was thinking of the mathematical physicists out there, and I was trying to say, or what I was thinking that didn't come out of my mouth was, this is why they conclude that light goes slower through a medium. That's what I was thinking. It didn't come out right, okay? So yeah, and here you have it. Here's a rope, okay? Rope. And we have the wave equation, C equals lambda times frequency, okay? And that means you're going to change wavelength for frequency or frequency for wavelength. That's it. Those are the only two variables. One goes up, one goes down, okay? That's all it is. They're inversely proportional. So what does that mean? It means that if you have many links, like in this case, what do we have? 4 links there, if you count the blue ones. Okay, you got 4 links. And if you untorque it, okay, then you have 2 links, okay, 2 blue ones or 3 maybe, and each link is longer, okay? And then vice versa, you torque it and you have more links, each link is shorter. And that's the equation of a rope. C equals lambda times frequency, a wavelength times frequency, okay? And that is the equation of a rope. So light always travels at the same speed. The only thing I want to clarify about that is that, the ultimate hypothesis, the ultimate assumption, or a secondary assumption, is the single thread. The single thread means that all matter in the universe is made of a single closed loop thread. Okay? And you might ask, and those who are more familiar with the theory, again, I recommend that people download the book to know what I'm talking about a little more, right? I can't go through all the details right here, right now. But those who are familiar with the single thread, they might ask, well, Bill, why didn't you just call your theory the thread hypothesis? And the reason is it's a secondary hypothesis. The main one is the rope. Why? Because we're concerned about things that are more close to us here on Earth, which is, light, gravity, magnetism. So we want to look at all these invisible things that Mother Nature does out there. We want to try to figure out how she does it, what kind of magic, or how does she do that, okay? And then the rope is appropriate because the rope explains light in one direction and gravity in the other, in a sense, right? What you have is all atoms are interconnected. They're physically interconnected by the electromagnetic rope, and that creates gravity. And along each rope, you have a signal going to the other one. So the rope hypothesis is a better name for the whole proposal than is the thread hypothesis. Okay, just want to clarify that. Okay, another comment that was made um, is this one here. If we can get it up here. Hope I get the right one. No, I got the wrong one. See, that's what. Oh no, it is the right one. Sorry, it is the right one. One fellow says spatial frequency equals. He clarified this. He said spatial frequency equals the number of occurrences per unit distance, cycles per length interval. And he said, on the other hand, temporal frequency is equal to number of occurrences per unit time, cycles per time interval. Yeah, and the only thing we need to clarify on that is no one uses the first one. No one uses spatial frequency except when they're referring to the vacuum, light in a vacuum. Then they use that. But then as soon as light enters a denser medium, then they use the bottom one. Why? Because they're going to use the refractive index version, which is this temporal frequency. What happens is they're going to maintain frequency constant, okay? And what they're going to do is shorten the wavelength. As you can see on the top one on the right, we have the waves going through a certain point in that line there, that certain point that we arbitrary point, and the one on the bottom also goes through that point at the same time. The only reason that can happen is that the ones on the top have to go faster. They have to go faster in order to catch up with the ones on the bottom, because the bottoms have less length. And so if the ones on the top have more length, they have to go faster to make up the difference. Okay, and so the one they use, again, they don't use the spatial frequency; they use the temporal one. And And so I wanted to show this, which is what I mentioned last time, okay? And that is that the refractive index, according to the mathematical physicists, is the one on the bottom, the temporal one. What they do, and I gave the example of the color red there, what they do is they hold frequency constant. And this is just, again, an example, 4.6 terahertz, okay? So that's the frequency. They're going to hold it constant when light enters a denser medium. In this case, the example is glass, okay? And what they're going to do is they're going to play around with a wavelength. They're going to shorten the wavelength, okay? Because the way they visualize this is that the wave of light is hitting a brick wall. You know, it's the car hitting the tree, okay? So that shock stops the wave. It just flattens it out in the direction of travel, okay? Which is what you just saw. And so they only play around with the wavelength. And one of the issues there is whether, the color of light changes within that new medium, within the denser medium. And that was what started this, the discussion, because one fellow put in there that the wavelength does not change within the medium, a denser medium. And I don't know where he got that. There's many people who say the same thing. He just picked up on one of those, said, "Oh, look here, it's proven." And so, yeah, that was part of the problem. That's where it started. And yeah, if wavelength changes, color changes, because color is a function of wavelength. And what these people are arguing is that no, color is a function of frequency. And so the answer to that is yes, too, as well, right? Because it does change in relation to frequency. Because again, what we're talking about is a rope, and so if the wavelength changes, color changes, but so did the frequency. The wave equation, C equals frequency times wavelength, cannot allow any other possibility. Okay. And on the other hand, refractive index is an artificial table that they've created based on pragmatic or empirical, experiments. And did they see the wave the wave flatten out? Did they see the frequency, etc.? No, they didn't. They calculated that, and they calculated it because they said, "Well, hold it. The wavelength had to flatten out because light travels slower through that medium." And why did they fool around with the frequency? Well, you asked them that question. They left frequency constant and they just shortened the wavelength. Well, with a rope, you can't do that, okay? Because if the links become shorter, right, you get more links, and vice versa. If you untorque, you get fewer links, but each link is longer. And so there's your frequency times wavelength, which is a constant, okay? Light travels at a constant speed through any medium. Why? Because any two atoms are connected by a rope-like architecture, okay? That's the theory we're proposing. And yeah, so here you saw the illustration of that. You can see that light waves are coming from the left on your screen. They're penetrating this piece of glass, okay, which is the blue in the center, and then coming out the other side. And one of the issues that people always ask is, how is it that the wavelength on the, how is it that light goes back to 300,000 kilometers per second when it exits the glass? That's a question that's often asked, and people don't understand the mechanism. And so what the mathematicians had to do was they say, look, the wave flattens inside the glass, but the frequency remains the same. And when it exits to the lighter medium, to air in this case, the wave goes back to its normal size. But this is all done, artificially. What they're saying is the wave flattens when it goes in and lengthens when it goes out. Okay, that's what they're saying. And another thing that many of them say is that when it's inside the glass, it doesn't change color, even though the wavelength, as you can see, is being flattened out in the direction of travel. So these are the issues that need to be resolved, okay? And since we have some other questions, I think we're going to be able to answer that, at least from our point of view here today. Okay, and here's the other question, or the other issue or criticism, etc., that was brought up. And we're going to get to that question I just asked. Okay, Bill states that color is a function of wavelength. No, I didn't state that. Okay, by this I'm saying not that I disagree. I'm saying that I'm the guy who states that. This, even before I was born, everybody said that color is a function of wavelength. Okay, and so that's the first issue that needs to be resolved. But let's continue here. But that cannot be the case, as the eye has no way to measure wavelength. Listen to what he's saying. He says the eye has no way of measuring wavelength. That's his belief. This is what he understands, or this is what his experience tells him, or what someone whispered in his ear. Okay, it must be the frequency of light that creates its color. Okay, and so yeah, the first thing is, I'm not the guy who said it. I was born in 1952, 67 years ago, and before I was born, we already had color as a function of wavelength. And I did include, because these people, I don't know, they're not paying attention. So I'm going to put it one more time. Okay, here it is. And it's the spectrum. Okay, that's the spectrum of light. Did I create the spectrum? No, this spectrum has been around for a long time. The spectrum was created by Mr. Isaac Newton, 17th century. Long time ago, like 400 years ago. So we've known about the spectrum since that time. When did we come up with the notion that that light is related to color? That color is related to wavelength? Where did we come up with that notion? Well, we came up with that notion from this gentleman in 1801. His name was Thomas Young. Okay. And he wrote, he didn't write, he gave a lecture at the Philosophical Transaction Royal Society in London. He gave it in 1801, and it was published 1802. And he, if you look up the original source, which is what I did here, you'll find that Young printed, in other words, or he published the length of the waves. There you see it in the first column, that 40266 in terms of inches, okay, then 256, 246, 240, 235, down all the way to 167 at the bottom. He measured the wavelength of light 200 years ago. And this fellow is saying what? He's saying, let's see, he's saying what? We have no way of measuring wavelength. Here we have a guy who 200 years ago measured the wavelength. You say, oh my God, how could he have done that with such low technology? I mean, was he a genius? Well, yeah, Thomas Young was a little brighter than this fellow for sure. Thomas Young used a caliber, okay? And he measured a very fine caliber, right? And they did have microscopes in those days as well, by the way. Today we have a SEM. We can see it a lot better. In fact, I have I think a picture here somewhere. I'll look it up later. Anyways, here's Mr. Newton. This is where all started. He started this mess, okay? So you got to blame Newton for this. And what Newton did, he passed white light through a prism. And you can see already that within the prism, okay, this is an actual picture, okay, the light is already changing colors. And when it comes out, as soon as it passes the interface with air, it's already broken up into colors of the rainbow. Okay, so first of all, it shows that light does break up already into colors within the denser medium, which destroys a lot of the notions that people have out there. And here's another picture just in case. Okay, this is a different picture, but again, it shows something similar. Okay, you can see that light goes through the prism and it breaks up into colors within the prism. Then it goes back into a second prism, which turns it into white light when it comes out of the other end. Okay, and you can see light is already breaking up inside the prism. So light does break up within a denser medium. And it better be, because the reason it breaks up is it's related to wavelength. And as you can see in the put this back up here, the spectrum, okay? You can see in the spectrum is based always on wavelength. Nobody uses frequency, at least in the industry. Everybody uses wavelength. In fact, if you just look up spectrum, okay, don't take my word for it. Look up spectrum and you will find that everybody puts it in terms of wavelength. Some people put it in terms of frequency, but 99% of the people put it in terms of wavelength. And at the bottom, you see my version of the spectrum, which is the rope. You can see the rope matches perfectly with that, so we have no quarrel with the rope having longer lengths and matching with a color spectrum. Okay, so why? Because C equals wavelength times frequency is the equation of a rope. That's the wave equation, so-called wave equation. It's the equation of a rope. In terms of the speed of light, little c is 300,000 kilometers per second. That's the speed of light. I'm saying that that one applies to the rope. There are other equations for, or this same equation can be applied to other types of waves, okay? So I want to make sure that's clear. But this specific equation, the velocity of light equals frequency times wavelength, is the equation of a rope. There's no other possibility. You cannot mimic, you cannot simulate that equation with anything other than a rope, as far as I can tell. Maybe you can do it with a chain, I don't know, a coaxial cable, a wire, I don't know, but for sure with a rope. But you can't do it with the wave, the transverse wave, and you can't do it with the particles. Particles first, you can't explain why the particle would go up and down. What takes the particle up, what takes it down? And a wave, there's no such thing as a wave. You don't bring a wave, a transverse wave, to the conference. See, I can bring a rope and I can tell you what light looks like. It looks like this. It has this kind of structure, DNA. That's what it is. Wave, what are you gonna bring? Everybody's gonna ask, what is the wave made of? And all transverse waves are made of particles, the ether. That's it, we're done. That means we're back to particles. And if it's particles, you gotta explain what takes the particle up and what takes the particle down for that sine wave, okay? So yeah, that's the big problem that wave theorists will have. Okay, and why did this come about? Well, one fella said that light changes color, remains the same. The color of light remains the same going through a Bose condensate, Einstein condensate. And here he thinks that this was real, that this was a film of a photon. So no, this is make-believe. This what you're looking at is a cartoon, and that's why they left the color in the of light of the photon. They left it the same, but he thought he was looking at the real thing. Okay, so that's why it came about. Okay, another comment came up that was made. Again, your recounting of the official version of why light slows in glass is incorrect. He accused me, slaps me. Okay, the reason is because light is an electric field that affects the electrons of the material in which it is traveling, causing the electrons to move. As the electrons move, they create an electric field wave of their own, which affects the light wave, causing it to move slower, which is exactly what I said. So this guy wasn't paying attention. He just repeated what I said and said, see, you didn't say how it really works. In fact, I illustrated. First, a lot of these people send me to a video, the one that they all reference. And that video I did, let's see if I get it right. Where is it? Here. This is the video. And I took this piece out, and you can see it tells you there why light, according to mathematical physicists, okay, why light travels slower through glass, 2/3 slower, and it tells you there, right there. Here, the electric field is a combination of light and the electric field of the electrons. So it's the electron field, the electric field of the electrons, which are slowing light down. That's what I said. And so this guy wasn't paying any attention, so who knows what went through this tiny brain, okay? He should pay more attention. In fact, I illustrated, and here you see the illustration. You see light waves coming in from the left. They go into the glass, and those that red waving, that's supposed to imitate the electron, the electron field. So light affects the electrons in the atoms. They create waves, and somehow those waves slow the piece of light that goes through the glass. And what is it doing? It's shortening their wavelength. That's what's happening, okay? It allows the frequency to continue without any problem, but it shortens their wavelength. And if you still have problems believing that, then what we do is we show you that what is written in the Wikipedia and what everybody essentially says. This piece comes from, the first two come from the, what is it? Let's see, I think I wrote it somewhere. The Stack Exchange, the first two comments, and the third one from the Wikipedia. They all say the same. What flattens is the wavelength. It's the wavelength that's flat. What's flattening it? The field of electrons, which is waving. It's waving. Why? Because supposedly the waves of light hit the atoms of the glass. So it shakes all the electrons. Now the electrons are all shaking, right, creating a wave, and that wave interferes with a smooth passage of light, slowing it down. What does it do? It flattens the wavelength of light, and so light travels slower, according to mathematical physics, not according to me, through the glass. When it comes out, since the electrons are no longer there to vibrate, it continues back or returns back artificially by magic wand, because there's no reason why wouldn't it not remain flat after that? Why would it expand again to a normal wavelength? What takes it back to a normal wavelength? That's what you got to explain. See, if the piece of glass shortens the wavelength within the glass, right, of light, right, why would that wavelength expand again once it goes back to air? I mean, please explain the mechanism. And of course, they will not be able to explain the mechanism either in air or in the glass, because there is no such thing as a wave. Wave theorists are people who have mental problems, because there is no physical standalone object called wave. A wave in the ocean is made of water. A wave of a flag is made of cloth. What is the electromagnetic wave made of? In other words, you have to identify not the movement, which is the wave, you have to identify the object. In this case, it's the ether, obviously. That's what everybody's thinking, but nobody mentions it, okay? But yeah, so this is the issue. The issue is that I did explain exactly the new version, and this is for the third time I think I'm explaining, but a lot of people are quite dense, and they're not following through, they're not understanding what's in front of them, what's visually in front of them, okay? Okay, another comment. And here's the comment. I like this one, I think. Invisible ropes are things, objects. All other hypotheses are conceptual and do not exist because no one has ever defined existence. So saith Mophead Muppet. This is like watching an episode of Gilligan's Island when the professor is off boinking Ginger and Marianne. You're a moron. I'm going to get a copy of your book just so I can burn it on video. Absolutely love the guy. Okay. Another guy says waves are in fact objects. Waves are objects? And another one says, since you're vehemently against concepts, what is magnetism? An object? So you can see all these fellows, you know, they haven't been around. They don't understand what we've been saying in this channel at all. It's like a hit and run. They just came in, listened to something that offended them, and they just said, I'll show you. Okay, so what are the problems with these? Well, the problem is that these people, you know, don't know, can't define the word object. That's the problem, okay? So here it is. Let's put theirs back up. So we have them next to one right next to another. What's the issue? The issue, these people don't know how to define these two words, object and exist. And physics is the science of existence. Physics only tries to explain those things that exist with things that exist. So you have to make an assumption, especially about the invisible, intangible mediators that Mother Nature uses. Okay, that's the issue. You have to use your common sense and say, well, how could Mother Nature be doing this magic trick? And of course, if they're intangible and untouchable, you're not going to figure this out through experiments. and which is what these people have in their mind. They're saying, hey, let's go to the lab and see it. We can see and touch it. Okay, and yeah, if physics is the science of existence, only objects may be said to exist, okay, because the definition is exist is equal to physical presence, object that has location, and you can't do physics without an object. So yeah, these are mandatory definitions to do physics. And these people want to skip the definitions. As you can see, no one defined it. They just say, oh, you know, it's like, we know what the word object means, and we know what a thing is, and we know what exist means, but none of them defined it. And they can't, and they won't, because no one has done so in 10,000 years. Why would these tiny brains be any different? Okay, so this is the issue. The issue is that you got to define. Okay, and here's another comment along those same lines. And this fellow also got a little upset. Apparently, this channel offended his religion, raped his virgin, as I say. Okay. I love how you demand that physics objects be made out of something physical. No, but okay, let's continue. But you never tell us what your so-called ropes of light are made out of. And see, he's focusing always on made out of, okay? Why is that? I mean, they're obviously not literal ropes made out of, right? Hemp fibers or nylon, right? So what are your ropes of light made from? Okay, it's always made. If you can't tell us, then I guess we can just discount them as not existing. Oh, the word exists. Why do we always bring that into these conversations? We always bring what an object is and what existing means. And for those of you who've been around, you can see that these are the key words that everybody's going to use. You can't avoid it in physics. Everybody's going to talk about whether a wave is an object and whether it exists, whether particles exist, whether space-time exists, whether black hole exists. Is it an object? Object and exist, object and exist, object and exist. You can't avoid those words. And see, and nowhere does he define either object or exist, okay? Every rope I've ever seen I could touch, okay, great. And bend and tie in knots and physically interact with. So if light is a rope, you should be able to show us. Show? Yeah, here, I'll show you. Here's the rope, okay? I showed, okay? I did the show part, show, and I'll do the tell later. By taking a light beam and tying it in a knot for us. We will wait here for you to post the video of you tying light in a knot. Okay. Also, how does a rope of light pass through a solid piece of glass? I mean, I've never seen any rope that could pass through a solid, except perhaps as a magic trick. Is that how it does it? Magic? Okay, let's answer this fellow. What's the problem with all this? Well, the problem is he never defined the word object. Okay, that's the problem. So we don't know what he means by object, but he insinuates, not formally defines, but insinuates that it has something to do with touch and with see. And also made of. He's talking about what is it made out of, okay? Or what is it made of or whatever. And we've already discussed that, okay? And obviously he hasn't been around enough. And there, right there in the middle, you see the word made of. The term made of. Yeah, none of these can serve as criteria for defining an object for the purposes of physics. This is not ordinary speech. This is not what we think of normally in the streets about the word object or what a thing is, what a medium is, what an entity is. Now here we have to define it very stringently as that which has shape. Okay? And so, yeah, you see see, touch, and made of. Made of we call mereology. Mereology is religion. Anyone who asks, what is it made out of, is talking about religion. That's what it is, okay? And so, yeah, what we have is what we call the golden principle, okay? The golden principle, what is it? You can't do physics without an object. So you must define the word object. How do we define it? That which has shape. Now, do you see any provision for made of? Do you see any provision for see? Do you see any provision for touch in that definition? And hopefully you don't, because that which has shape has nothing to do with see, with touch, or with made of. Is a table what it's made of? Is that what a table is? You know, here comes the Martian, you know, Klingon comes to visit us here on Earth. And he has, what is a table? Well, a table is a gazillion atoms. Oh, what is an elephant? Well, that's a billion atoms. What is a house? That's quadrillion atoms. That's what they're made of. Is that what an object is? What it's made of? So what are the objects? What are these atoms or things that make up these big things? Aren't those objects too? An object is the object it's made of. Is that what the definition of object should be? Is it that which you can see? Is it that which you can touch? Well, we can't see the air. I mean, does that eliminate the air as a physical object? Not in physics. Maybe in ordinary speech. But for the purposes of physics, air is a physical object. Water is a physical object. And you say, what are you saying? What are you saying, man? What do you mean air is a physical object? Yeah, because you're bringing your notion of ordinary speech. For the purposes of physics, air had better be an object because first it's made out of atoms, but forget about that because that's the made of definition. We're talking about air as a body or water as a body. Okay, when we say water, when we say air, and all you got to do is have the astronaut, put water in a little balloon, right? Take it out there in space, stick his hand outside the window of his spaceship, blow it up, right? And suddenly you see this blob of water, just expanding in space, right? And someone might say, well, that's an odd shape. I don't know. What is the shape of that? That's the wrong question. The question is, does it have shape? It's a yes or no type of question. We have to ask whether God has shape or whether God does not have shape. If God does not have shape, God is a concept, and that's what you're praying to, a concept. Hopefully he's listening. If God is an object because he has shape, well, then at least you have something that could exist if it has location. So yeah, water is a physical object, and water does, that blob of water that the astronaut released, that has shape. And so does the air that he would put in a balloon. If we could see it, if we could color code it, he pops the balloon in the middle of space. That blob has shape. And we call that blob whatever shape it takes. We don't care if that blob has shape. And here on Earth, we have the shape of air, and it has a shell shape enveloping the Earth. So air does have shape. Yeah. It's a yes or no type of question. Does air have shape? Yes. If it has shape, it's an object, period. For the purposes of physics. We're not talking about ordinary speech here. You can keep your ordinary speech in your Sunday school. Don't bring it here, okay? And so here was this thing that this other fellow said. He said, "Oh, we can film." See, here's proof that this guy's asking. He's saying, "Look, here we film the photons, right? They're going right through the air, and they're going through that blob there, right, and going slower through the blob, and so we filmed the photons." Well, if they filmed the photons, you can be absolutely sure that they have not filmed light. And the same goes for this fellow. He says, "Bring it over here. Show me that you can tie the rope in knots, the rope of light, right, in knots." Well, he's only defeating his own argument, but he's not smart enough to realize that. Because what he's saying is that here Mother Nature made something which is untouchable, unseeable, unsmellable, untastable, unhearable, and he's going to go to the lab and he's going to try to prove that you can't touch light and you can't see light. Well, yeah, we know that. But if he's successful, or if I were successful, right? If I could go to the lab and say, "Look, I tied the rope in knots," you can be sure the rope is nonsense then, because we're not supposed to see or touch the rope. Okay, because that's not the definition of an object. An object is that which has shape, and a rope has shape. And so does the architecture of the medium that serves as a mediator for light, the agent, the secret agent that Mother Nature uses. If I could touch, if I could see that mediator, if I could tie it in knots, as this guy says, for sure, then the rope cannot be the mediator of light, because Mother Nature specifically made it invisible and intangible. Because if she had made it tangible, we'd be tripping over all these ropes. Not to mention if she made them visible, we wouldn't see anything other than ropes in our eyes. Okay? So yeah, see-touch is not the right criteria, but these people are stuck on this see-touch thing, and they say, "Oh, how can a rope go through each other? Don't they get tangled?" And the question is, why did they ask that about quantum? I mean, quantum says, look, all these particles go through each other. You can have many particles at one location at the same time. You can have one particle at two places at once. And nobody questions that. Nobody asks that question over there. Nobody says, how can two particles be at one place at once? How can one particle be at two places at once? Okay, so like President Kennedy once said, he said, ask not how a rope can cross against another, through another, or how two ropes can occupy the same space. Ask how two particles can occupy the same space or be at two places at once. That's what Kennedy said, okay? So that's what you should address. You should worry about, explaining quantum first before you come here and talk about the rope. If you can do it with quantum, explaining how two particles can be at the same place at the same time, or how a particle can be at two places at once, two different places at once, fine. Then you can start asking that question about the rope. First let's answer quantum, so we make sure you don't return to quantum ever again. Okay, let's make sure we cross out that possibility first. Okay, here is another comment. And it says, the ether is not a bunch of particles. Again, people are offended because I define ether as a bunch of particles. Another person says, the ether is a world used to identify the medium that fills everything. For sure, cannot be bumping particles. See, none of them tell you what the ether is. Everybody just tells you what it ain't. And that should make you stop and wonder, why don't these people define, what ether is? And so I had to define it for them, and I defined it as a bunch of particles. And here I made, here you have a vision of what the ether has always been, what everybody has always understood by the ether, except people who never worried about definitions, who never did any investigation on the ether. They just use the ether, they just run along with it, and they say, well, the ether is a bunch of waves and a bunch of particles, and who knows what concepts are in there. No. The ether has always been a bunch of particles. It's always been treated as a bunch of particles, especially in the 19th century, which was the century of ether until it died, supposedly died, at the beginning of the 20th century. And all they did was really convert the ether into space-time and a false vacuum and all these other fancy words that they have today for the ether, because the ether is still around. That's the problem. And here's the ether, okay? See if I can put it in here. Give me a second. Somehow I lost my ether there. Where did it go? Okay, I got another ether. No problem. Give me a second. Here's the infinite ether. Okay? The infinite ether occupies the entire universe. It has no end. Okay? And if that's the case, then the ether is not an object, because an object is that which has shape, and this one doesn't have shape. I only have shape now only because I had to put a square around it, but otherwise this thing is supposedly what they call infinite. And there's no such thing as an infinite object, because an infinite object violates the definition of the word object. An object is that which has shape, and this thing doesn't have shape because it's infinite, right? So there is no such thing as an infinite object. Okay, so here's the finite ether in the alternative. Okay, that's the infinite ether. You can choose to have this one. Here's the finite ether. So we have ether, and somehow there's this black stuff, whatever that is, that continues. And of course, you have to identify the black stuff. We don't care about your ether, your particles there. We want to know what the black stuff is. What are you going to put in there? And one of the problems that we have with the ether is that people want it two ways, and they don't understand this. So I try to make them pay attention, but they don't. So this is only for intelligent people. People who are not intelligent, don't listen to what I'm going to say next, okay? Just get out. And this is the issue. Is space a container? Okay? Is space a container? Like a box or a cylinder where you put gas or something like that. Is space a container? Does space contain particles, or is space made of particles? We have to clarify that. So the guy who comes in with a proposal of particles, of ether, he has to tell us one or the other. Is your space, is your vacuum, is your nothing made of particles, which is what quantum mechanics says, okay? That space is made of particles. Photons, primarily that's what they have in their mind. Or the space contain particles, meaning that space is something else and it contains all these marbles in there. And you got to clarify this. And see, they never do. You can't pinpoint them because they run away. Everyone runs away. So that's the question they have to answer. Is space made of particles, or is space, or does space contain particles? Does space contain marbles? Because then in that case, they have to tell me what space is. They have to define the word space or vacuum or nothing or whatever they want to call it. Okay, so this is the issue, and until that question is answered, we can't continue because we're talking to irrational people. Okay, here's the ether in terms of waves, because some people say no, it's waves. Okay, here's your waves. Here's the infinite ether made of waves this time. Okay, and again, it's not an object because if it were an object, it would not be infinite. Okay, and so then we have to make the ether, the finite ether. Now we have, again, this black stuff that surrounds the ether. Ether is in there, and that's we're inside that universe where you see all those waves. We need to know what the black stuff is. That's what we need to do. And in that case, you got to tell me what the black stuff is, and if it's a container, or if it's made of waves, or or particles, or whatever. And this is the issue. The issue is that all these people elude these tough questions. No one pinpoints and stays 2 years analyzing the ether. What is the ether? Okay, and they say, they do hand waving, and they just want to continue and say, I'm going to use the ether. No, I don't want you to use it. I want you to define or point to it. And if you're going to point to it, I need for you to illustrate it, and it better be finite. It better, and then in that case, you got to identify what encapsulates the ether, what that black stuff. Okay. So these are the issues that all these people avoid. Okay, here's another fellow, moving on here, and he brought a comment from Mr. Newton. He said some choice quotes of Isaac Newton, and I'm not going to go through all the details here. You can look at it later, But essentially, what Newton emphasized were hypothesis. The word hypothesis shows up a lot in his language. He talks about certainty, which is an opinion, means that you have certainty, you believe, you have proved it to yourself. Talks about experimental philosophy, has nothing to do with science, not the philosophy part, but the experimental part. We don't do experiments in science because we cannot. First of all, we don't do experiments because we have to explain experiments, not do them. Anyone can do an experiment. I can drop a pen 100 times. It's a repeatable experiment. I can measure. And does that mean I can explain why the pen falls to the floor? Okay, so this is the issue. The issue is explaining. That's where you have to break your head. But to describe and say, yeah, I dropped the pen 100 times. I did the experiment. And so what? What did you learn? That's the issue. And so experiments have nothing to do with physics, aside from the fact that experiments will not tell you what light is. Okay? We did all the experiments we ever needed to do about all Mother Nature's invisible mechanisms. We did experiments on electricity, on magnetism, on light, on gravity. We did them all. I mean, maybe there's one experiment we forgot more in the bag of marbles. Maybe there's one more marble in there. Okay, fine. Maybe we missed one or two. We did all the experiments we ever needed to do. We don't need to do any more experiments. We need to explain. Now we need to know what gravity is. We need to explain what gravity is. We need to explain the mechanism of gravity, how Mother Nature does that trick. And this is what these people don't understand. They say, no, let's do an experiment. Let's go to the lab. Let's go to the field. Let's run another experiment. For what? What are you going to run? We're done with the experiment. Now we got to explain the experiments. Okay, we have to explain what we observed. You like observation? Okay, we already observed everything. Okay, now we need to explain, why a pen falls to the floor. Very simple experiment. Just you can do it at home, always in the presence of a relativist, right? Let go of a pen, you'll find out it falls to the floor. You did the experiment. It's a repeatable experiment. Anyone in the universe, anyone on planet Earth for sure can do it. Now explain it. Explain why that pen falls to the floor, not to the sky, not to the ceiling. And hopefully you will not use a concept called mass or another concept called force or any of the nonsense invented by mathematical physics. No, what you have to do is explain it in mechanical terms. You have to, hopefully you're using objects and not, spirits and angels and God, magic. No, you got to explain it with objects. You need a mechanical explanation. You need to illustrate. You need to make a movie of how Mother Nature does that experiment or that phenomenon. Okay? And that's the problem. The problem is that Newton was a very influential person, especially in the following century, in the 18th century, until he died, I think 16, am I saying that right? 1728, something like that. But he was very influential, even after death. So that's the problem, because he, among others, another one was Galileo, they insisted a lot on experiments, on math, and none of that has anything to do with science. Science explanations. We don't use math to explain, okay? You can't explain with math. You can only describe with math. So yeah, unfortunately, Newton took us on the wrong path, and that's why we have very little respect for Newton. Okay, another comment. And this one shocked me a little bit. If two objects were identical sphere shapes and they were attracting towards each other, would they accelerate? Because I don't see how the ropes could fan out. It really struck me because this is something we should all be able to visualize. And so what I did was create a little GIF here. See if I can find it here. Where is it? There it is. Always have so many of these. Sometimes they're hard to find. And so here you see it. Okay, you have two balls equal size. These balls are made of atoms, okay? Let's make sure we understand it. Every atom of one ball is connected to every atom of the other ball. I only put two ropes there, two connections. It doesn't matter if they're ropes, whatever. I just put two connections, okay? And one object is attracted to another. Now I just want you to look at the angle of the ropes. You can see that the angle changes. And if you put a gazillion ropes between them, you're going to, between every atom of one object and every atom of the other, you're going to see the same event. You're going to see all these ropes, just changing their angles. So they're not pulling on the same axis. Okay. And yeah, it's up to you to put all the other ropes in there. I didn't take the time. But with this, if you can't visualize this, well, I can't help you. This is straightforward as far as I'm concerned. Okay. And here's another version of it, which is what I explained, I think, one or two videos before. And it's an astronaut falling to Earth. And here you can see the ropes. As he falls, the ropes fan out. So I'm not sure what is so difficult to understand about the mechanism that is being proposed by the rope model. The ropes fan out as the guy falls to Earth. Okay, because every atom in his body is attached to every atom that makes up the Earth. Okay. So I don't know, I can't help you any further. If you can't visualize that, well, I'm out of luck. Okay, just wanted to cover a couple more points. One is that Mr. Tanimura, the other day, I brought him up, he claims to have handled one electron at a time. Okay, he did the slit experiment with electrons, with electricity essentially, right? And he claims, the second guy to claim so, another guy was an Italian group led by a fellow by the name of Merli. And years later, this guy came out, he said, no, I was the first one. And so he handled one electron at a time. So he says, okay? And this is what he said. I pointed this out the other day, okay? He just went in there and shot these. He says, you can be sure these are individual particles, these electrons. He shot them one at a time. And yeah, anyone who looks at this says, yeah, it looks like he shot them one at a time, right? Because look how he's building all that up. So we have a lot of problems with this. The first one is, did he did he? I mean, he's pretty good shooting, you know, at shooting. He's got this gun, and he's gonna shoot on the screen, and he's gonna put each bullet exactly where he needs it. You know, that's pretty good shooting. I mean, you try to do it at a shooting gallery or um you know, somewhere where they have guns and you have a target. Try to see if you can hit them in such a way that you build these fringes, like here he did it here. See, you're going to build that shooting one electron at a time. You know, that's kind of hard to believe that he did that um, by pointing. I mean, no two electrons fell in the same spot. He built that one atom at a time, one electron at a time. You know, how did he do that? And especially the issue is, you mean the electrons just fell in such a way that they built these fringes one at a time? Why didn't all these electrons fall in the same spot? Okay, that's one issue. But then the other, more important, more basic, is the electron. The electron is alleged to be a zero-dimensional, no-volume nothingness. There is no such thing as an electron. And here's proof. Those people who want proof, okay? See if I can find it here. Here's the electron. It's called the no-size electron, as I call it, okay? And what do you read there? Oh, holy. And this is what you're going to find. Electrons are, this is from the Wikipedia, it says, electrons are generally thought to be elementary particles because they have no known components or substructure. And in particle physics, an elementary particle or fundamental particle is a subatomic particle with no substructure, thus not composed of other particles. Okay? Then you look up another version. It says when an electron looks more like a particle, it has no shape, according to the standard model. In this context, physicists call an electron a point particle, okay? Meaning that it interacts as if it is entirely located at a single point in space and does not spread out to fill a three-dimensional volume. And when you look up point particle, it says, point particle is an idealization of particles heavily used in physics, yeah, maybe in religion. Its defining feature is that it lacks spatial extension. Being zero-dimensional, it does not take up space. So how did Mr. Tanimura handle a nothingness known as the electron, right? He says he handled one electron at a time. Maybe he handled spirits. Maybe he pushed angels. I mean, how does he know he handled one electron at a time when they say that it's got no volume, it's got no size? We're talking about a zero nothingness. That's what it is. And he says he handled one of these at a time. But then we have a bigger, even more fundamental problem with Tanimura's version, and that's, here it is, the planetary atom. You know, in order to handle one electron at a time, this is what he relied upon. He relied on the orbiting bead model of the atom. He's saying an electron is that little bead that's going around the atom, and that he was able to manipulate that little bead. Well, you know, it's like I said last week. What they have to do is, Tanimura and all the quantum mechanics, is just draw a picture of the atom. All I need to see is an atom, okay? And here's what they need to specifically draw, which is what we're interested in, and that's that brown stuff there. We need to know what is between the electron and the proton, or the nucleus if you prefer. What holds the electron? What binds it to the nucleus? Why does the electron stay there before he handles it and uses it to do ionization or electricity? We need to identify that region there, okay? Now, Tanimura claims that, you know, there's no other possibility of interpreting what he did except shooting one bullet at a time. And again, we challenge that. See if I can find it here. Here it is. And here, there is another mechanism, and it's the bullet versus the drill. Did he shoot bullets at the wall, or did he drill holes into the wood? I mean, which one did he do? Is the bottom one a valid mechanism also for doing electricity? Or should we just say that electricity is the shooting of bullets? And again, if he's going to do shooting of bullets, he's got to first illustrate the quantum atom, and he can't do that because what's he going to put between the electron and the nucleus? That's the question that he's going to have to answer before he can make a claim that he handled one electron at a time. Okay, and here you see uh, the different notions of electricity that are out there. Okay, the first one is the you could call it the classical mechanics. That means that you have atoms and you have all these electrons flowing from atom to atom. What quantum has done is gotten rid of the atom itself, and it just shoots electron beads, and they say electricity is just a flow of beads of electrons. And that's what Kanamura is saying. He's saying that, every electron he handled individually, and he can play around like playing with marbles. He can handle this and push it any way he wants. And what is the problem with that? Well, the problem with that is that if you're going to do electricity, I worked quite a few years in this field. If you have a vacuum chamber and you pump it down, we pumped it down usually to 5 to the minus 7 torr, and there's hardly any material in there. There's quite a bit, really, as we found out always. There's quite a bit of material in 5 times 10 to the minus 7 torr, okay? But for all practical purposes, that's a clean chamber. That's a pretty clean chamber. What we do next is we fill the chamber with argon, an inert gas. And when you do that, now you raise the pressure back up to the minus 3 torr level. So you were at room pressure, right? You bring it down to 5 times 10 to the minus 7 torr. Now you bring it back up to close to room pressure. In other words, at minus 3 torr level, you go back, right? Because you put more garbage in there. You're going to put argon in there, right? And now you can have electricity flowing. At minus 3 torr level, you do have electricity flowing. I swear on my mother's grave, okay? You do have electricity flowing. You have that situation. Now pump the chamber down. You pump all the argon out, little by little, gradually, and you don't put any more argon in. Okay? So you're going to vacuum the chamber back again. You're going to pump it down. So you're going to go to minus 4, minus 5, minus 6, minus 7 torr. Hopefully you can continue all the way to minus 12, which is what we have on the moon. And the question is, will electricity continue flowing when you do that, when you remove the atoms? You would think that now electricity should be easier. The electrons have nothing to block their passage, okay? So now the mean free path of the electrons going from cathode to anode should increase, okay? And so now it should be easier to run a current. And that's exactly not the case. It's the opposite. You need to raise your voltage. The more material removed from the chamber, the more voltage you need to get that electron bead, supposedly, right, to flow across the vacuum to the anode. And so that defeats quantum mechanics, because quantum mechanics says that if you remove matter from the chamber, the electricity, that's the prediction. That would be the prediction using that term that quantum mechanics uses. The prediction should be that now electricity should flow smoother because now you removed all the obstacles. Because you don't need atoms in the religion of quantum mechanics. All you need is to send beads through the vacuum. And that's not true. That's definitely not true. Don't take my word for it. Go out there and verify it with any guy who does vacuum. And you'll find out that if you remove matter from the chamber, you have to increase the voltage. But if you leave voltage constant and you remove matter from the chamber, the electron beads will not flow. You will not have electricity flowing. Okay, don't take my word for it. Just go out there and do your research. You'll find that that's the case. Okay, I'll go over the line a little bit this time around. And just want to leave you with this thought, which is also related to the atom. What does an atom look like? And it's got to do with the quantum numbers. Okay, quantum numbers, essentially you have the principal number, the magnetic number, and the azimuthal number. And these are numbers that give you an idea of what, when you apply them to Schrodinger's equation, it gives you the shape of an atom. It can give you the s orbital, which is a spherical orbital. It can give you the p orbital, which is the figure 8 orbital, right? You get all these orbitals by simply plugging this into Schrodinger's equation. That's why he became famous, because he was able to give you an idea what an atom looks like based on this equation, okay? In one sense, that was pretty good work, no doubt about it. So you get a situation that looks more or less like this. Let's see if I can put this up here. Takes a little bit to get these things up here, okay? Let's see if I can get it up here. Okay, so you can see what an atom might look like in reality in this invisible world of atom if you apply Schrodinger's equation to those numbers, including one that's missing, which is the spin. I'm not going to get into that today, okay? But if you apply those and you put them there, that would be the shape of this invisible thing we call atom. Okay, that's one type of atom. Here you get a whole series of them, okay? We can get this up here, okay? You can see the shapes as you apply Schrodinger's equation. So we are able to see this invisible world of atoms by simply applying Schrodinger's equation, okay? Now, how does a rope handle this, okay? That's the point that I'm trying to make so that you can take it for your own thought. Okay, here's the rope model, okay? And let me put the first one back up there. Quantum numbers, here it is, okay? We're saying essentially the same thing here, okay? We're saying that what Schrodinger discovered is not the movement, like the angular momentum or the different z and x and y directions of angular momentum. He thought he was describing an electron bead that is moving around in a region around the nucleus. And what we're saying is that the electron is really the whole shell that encapsulates the proton. And what Schrodinger's equation really does, it does give us the shape, no doubt about that, but what it is, it pinpoints a point, a location along the sphere, in this case the hydrogen atom, right, that encapsulates the proton. Okay, so all these numbers are applicable to the rope model just as much as they are to the quantum model, which is the orbiting bead, right? Which again, they can't justify why the electron stays tied to the proton. In our case, we have no problem because the model of the rope shows that the threads, one goes to the center of the atom, which is the nucleus, which is the proton in this case, and the other one coils around and forms the electron. It's really the electron shell. That's what we call it. It's a shell. And so the numbers that quantum uses, the azimuth, the magnetic, and the principal, these are simply locations that the mathematicians are pinpointing along that shell. Okay, so yeah, we do have a version of what are known as quantum numbers. And again, this is just for your food for thought so that you can apply the same equation, the Schrodinger's equation with all the quantum numbers. You can apply them just as well to the rope model, no problem whatsoever. So not only can we apply the wave equation to light, but we can apply quantum numbers which underpin Schrodinger's equation. We can also apply them to the rope model. Okay, with that, I will see you on Wednesday, and we'll see you then. And download the book. It's for free. Go ahead and read it, and it'll bring you up to speed on the rope model, different universe. You don't have to believe it. We only ask that you understand it. We'll see you on Wednesday. Bye-bye.